Welcome back. We are discussing about the sludge handling aspects of wastewater treatment. In this video, we'll be discussing about the sludge digester and different design aspects of sludge digester. So now if we look at this diagram, this is the sludge digester. You're having an outlet tank. Then you will have an inlet pipe. There is having a gas dome, and then you're having a sludge hopper where the digested sludge is coming down to the bottom. Now stabilized or digested sludge is now going out from the bottom, and then in the sludge digester, the advantage is digested sludge will be separating to the bottom of the conic hopper, and then afterwards above it you are having the raw sludge and seeded sludge is now there at this layer, and then the liquid and solids are separated out. The liquid will be going above this sludge mixer, and then the gases will be released due to destruction of volatile solids. They will be pushed to the top. While they are moving to the top, the fatty material which is present in the wastewater of the sludge, they will be pushed out here, and then what you are having is you are having a scum layer at the top. So here digested sludge, raw sludge plus seeded sludge, then liquid which is called as a supernatant level, supernatant layer, and then you are having a scum layer, then we are having a gas dome. All these are now stratified in the anaerobic digester or sludge digester. So this is your diameter of the digester, and this is the liquid depth of the digester, and that is nothing effective depth of the digester. This is sludge entry into the digester through pipes, and this is where you are collecting the sludge in the form of a digested sludge. And now the most important thing is the dome. The gas is collected in the top layer as a gas dome. So you can have a moving dome or a fixed dome. You can have a roller here. Once the gas is there, it will push the dome up, goes to the top. This is the minimum level and then the maximum level. Sometimes the gas dome is fixed here so that there's no movement also. So we'll see the different design parameters here. How to calculate the diameter, how to assume the depth of digester, how to estimate the gas in the digester. All these things we'll calculate. First of all, we'll see about the design period, detention period. Detention period in the digester. It is nothing but the time in which the sludge is kept in the sludge digester for the digestion. It varies on the operating parameters. So usually when we are maintaining a range of 20 to 40 centigrade mesophilic range and the average temperature retention of 30 centigrade, so 30 days of detention is provided for digestion of the sludge. And monsoon storage, once the sludge is digested coming at the bottom, when you're separating the digested sludge out, it should be dried out. But during monsoon period, we can't send the digested sludge out because it cannot be dried easily. So we have to provide an extra volume for the sludge digested during the monsoon period so that it will be stored within the sludge digester. After the monsoon, it can be taken out as per the need and the design of the digestion, or as per the design of the drying area provided for the digested sludge. So a monsoon period of 60 days is usually considered for a extra storage of the digested sludge. 30 days is the digestion period and 60 days is the monsoon storage period. Accordingly, we have to calculate the volumes. The depth of the tanks, usually 6 to 9 meters are suggested and a minimum 6 meters is preferred. Diameter of the tank, it should not be more than 15 meters. Higher diameter creates operational difficulties. Biogas generation is based on either volatile solids destroyed or volatile solids added. So usually we prefer the first option, volatile solids destroyed. So it is expected as 0.9 meter cube per kilogram of volatile solids destroyed. If you take volatile solids added, it is 0.6 meter cube per kilogram of volatile solids added to the tank. Sludge hopper, the bottom, 1 is to 1, 1H to 1V, horizontal to vertical, at a minimum of 10% when sludge clearing is periodical. So digester volume, how to calculate the digester volume based on the digestion period as well as the monsoon storage. There are two methods, linear variation and parabolic variation. That means whatever the sludge which is coming into the tank or digester is reduced or digested in a linear model. That means this is the initial period of the initial volume. Say this is a fresh sludge coming into the tank, okay, and this is your digestion period, say T. So during this period, this reduction of the volume from VF to VD digested. This is a linear form across the digestion period. So this is called as linear variation. For this, what we are trying to take is average of VF plus VD into TD by 2. VF is the volume of the fresh sludge, VD is the volume of dry sludge. By 2, we are taking average, and then into TD is nothing but digestion period, and plus VD into TM. This is your monsoon storage. TM is the monsoon period, usually 60 days, and VD is the digested sludge. This is a monsoon storage. You are keeping extra in the tank. The parabolic variation, what we are seeing is the same logic we are applying. So this is your VF. The reduction of VF to VD is not linear. So this is not linear. This is parabolic like this. So this is we are assuming. So this is your VD and this is your T period or a period of time T. So we are assuming that due to operational constraints and the volume of fresh sludge and the volume of digested sludge, they are not changing in a linear pattern. They are going through a parabolic variation. We'll assume that, and volume of the tank in this case is VF minus 2 by 3, the difference of VF and VD multiplied by TD. TD is the digestion period plus VD into TM. VD into TM is again monsoon storage. This is the monsoon storage for both these cases. The first term only gives you the actual volume of digestion, volume required for digestion, and second term is giving you the additional volume for monsoon storage. Volatile solids present on reduction. Usually, the fresh sludge, the volatile solids are around 60 to 70% of the total solids. Specific gravity 1.1 to 1.2. The specific gravity of the fixed solids in the range of 2.5 to 2.7. So during digestion, the initial 60 to 70% of the volatile solids, they are reduced by 60 to 70%, so that accordingly, these 60 to 70% solids, they are converted to the biogas or any gas here, methane, carbon dioxide, whatever it is. So this 60 to 70% reduced, they are converted to gas. The ratio of volume of biogas generation to surface area, usually 9 meter cube of biogas generated per meter square. This is how we have to provide. For 1 meter square surface area, this check value should not be more than 9 meter cube of biogas generated. So finally, this is the major design parameters we have taken here. Now we'll quickly look at some of the other options where the different types of digesters are used. So now you see this is the biogas tank. Now you can see here, this is a fixed dome type. So this is a gas dome. This is your gas dome. So now you can see this is the inlet. This is biogas. Usually the agricultural waste is coming here. In the place of sludge, we are putting the cow dung in the form of a slurry and allowing through inlet like this. This is the first chamber where digestion is taking place. And whatever the liquid is there, that liquid is now coming out. The supernatant liquid is coming out. That supernatant liquid is now exiting through the pipe into the outlet here. And whatever the gas collected will go to the top into the dome. And then we are having a control valve to collect the gas from the top, right? So this is the biogas digester, which is normally adopted in everywhere in India, in particularly in rural areas. It works under the same mechanism of anaerobic digester. And this is another floating type of digester. And what we are having is again the mechanism of operation is same, but the shape and configuration of digesters we are providing are different. So now here is a flexible material used here. So now what you are having, this a sludge is now entering into this inlet pipe. Now here at the bottom you are having a slurry. It should be coming in the form of a slurry, and the gas is generated, goes to the top, and it's separated out, and the liquid whatever is there, which is collected somewhere in the middle, and that goes out on the form of outlet. So it is now kept in a trench so that there is no backfill here. Some backfill is there, is not um, having any impression or compression from the outside surface. Is the inflated digesters. Now you can see this is actual pictures of the digesters. Now you can see this is the dome. This is the dome, and this is the overall depth of the digester. This is the foreground, and this is the digester here. And now there will be a ladder so that people can easily go to the top and monitor whatever the mechanism is required, or mixing operation, or temperature control, etc. And now this is another tank which is not connected to digesters. So these are the two digesters we are provided in the tank. You can see one more digester is there in the background. So you can see here is a pretty high from the above ground level, around 6 meters minimum provided, without going for too much height. If it is more than that, then it comes into difficulty in the operational part of it. So now this is another way of looking at these diagrams. So now you can see this is a dome in between. This is a dome here, two different types of domes provided here. And now the bottom you are having the digester. This is the digester. This is the control mechanism. This is the control mechanism. And then people can walk to the top by using a ladder, so that if we want to have any monitoring operations, they can do and then come back. So these are different types of digesters. It's not exactly in some places, and they are going even for some egg-shaped digesters. At some places, they are going for a hemispherical digesters, and then somewhere where they're going for a cylindrical digester with a hemispherical dome, a conventional. This is the conventional digester, and number of options, number of designs they are being made across different places, suiting to their own requirements, suiting to own their demands. But ultimately, whatever the design they take, and the net operation is there in sludge digestion, where the sludge is now separated into digested sludge, active sludge, liquid, scum layer, then gas. Gas will be there in the top. It collected in the dome, which can be floating dome or a fixed dome. And depending on that, the digesters are there in the operation. These digesters can be used for different types of wastewater sludges, maybe agricultural waste, and then food waste. Number of options are possible for that. So this is all about different types of digesters as well as the design parameters of digesters. Thank you.